Young's modulus is simply a number that we assign to materials to describe their resistance to change when a force is being applied. Some things compress very easily, other things are very hard to compress. If you look at this snapshot of the baseball bat hitting the ball, you can see the baseball actually compresses when it's hit with the bat. The wood bat, on the other hand, probably isn't going to compress enough for you to see it. That means the wood bat has a high resistance to change, or a high Young's modulus, and the baseball has a much lower resistance to change, so it has a lower Young's modulus. Many people simplify Young's modulus by describing it as a measurement of the stress divided by the strain. The stress is simply a measurement of pressure, which you can describe as the force being applied divided by the surface area the force is being applied to. The strain is measuring how much the substance compresses. In Young's modulus, we actually calculate the percent change, which means you have the change in the length divided by the original length. So when you take the force and divide it by the surface area, and divide that by the change in length over the original length, then you get Young's modulus. Once you have identified the Young's modulus for a substance, that number does not change very easily. So once you've identified the modulus of, say, of diamond, say at 1050, whether the diamond is big or small, skinny or fat, it doesn't matter. That modulus is not going to change. It's constant. The only way that a modulus can change is if you apply heat, and often a lot of heat. A good example is when the World Trade Centers collapsed. You may remember the discussion that the towers did not fall because of the impact of the planes. Instead, it was the fire. The heat from burning jet fuel, enormous heat, lowered the modulus of the steel. The steel was allowed to bend and compress, and eventually the buildings fell. Similar to Young's modulus is a concept called shear modulus. Whereas Young's modulus tested compression from a downward force, shear modulus tests the bending motion from a sideways force. And the equation for shear's modulus is very similar to Young's modulus. The shear modulus is equal to the force divided by the area divided by how much the substance bends to the right over its original height. And just like Young's modulus, once the shear modulus is set for a substance, it's going to equal a number that doesn't change unless, of course, we add heat. So here's a fairly standard Young's modulus problem. We'll use the standard equation of the force over the area divided by the change in x over x. This time the equation is asking us for the percent change, and the percent change formula is really just the change over the original, which happens to be the denominator of our equation here. So in this case, we could just rewrite the equation as the force over the area divided by the percent change. And that's going to be equal to our Young's modulus. Now we just plug in the numbers. So our Young's modulus, which is 9 times 10 to the 9th, that's going to be equal to our force. That's going to be equal to our force, which is 5.4 times 10 cubed, divided by our area. Now our area is written in centimeters, so we have to convert that to square meters. And since there's 10,000 square centimeters in a meter, we can write our area as 4 times 10 to the negative 4. And then that's going to be divided by our percent change. Remember, your test is going to be a multiple choice test, so you can usually do a lot of rounding, especially in these large fractions. So we can take our 5.4 divided by 1.3, and that's going to be roughly equal to 1.3. I'm just estimating here. Following our rules of exponents, we take the 10 to the negative 4 and move that to a 10 to the positive 4 in the numerator. The next step is to get rid of the p in the denominator, and we can do that by multiplying both sides by p. So now our equation is 9 times 10 to the 9th times p is equal to roughly 1.3 times 10 to the 7th. Divide both sides by 9 times 10 to the 9, and we get 0.14 times 10 to the negative 2. But we're not done yet. The question is asking us for a percent, not a decimal. To convert a decimal into a percent, you simply multiply the decimal by 100. So in this case, we have 0.14 times 10 to the negative 2 times 100, and the 100 and 10 to the negative 2 cancel out. So we're left with 0.14%.